For this project, a communication link was designed using a wireless propagation model and taking into consideration quality metrics in a marine environment. Using these metrics, the maximum link lengths and the reliability of the link was determined. These values were then used in a simulation to determine any inaccuracy in our model. These following assumptions were made in designing the link as listed on the slide. The significant points are that the majority of the sea has no obstructions, and temperatures are uniform above seawater. This slide shows the technology to be used in our design. These figures are also important in choosing our propagation model. Furthermore, we will be referring to these requirements in any calculations made. Here is our table that we would use to determine what design seems most applicable to our environment and our technologies. From observing the operating frequency column and keeping in mind that the frequencies we are dealing with are 5.8 GHz, we can see that the free space path loss model and the Longley-Rice model are our two options. The ITUR may seem desirable as it considers CPATs, but even if we were to use a frequency of 2.4 GHz, we would need a considerably large base antenna. Anyways, the free space path loss was chosen between the two, as we have considered the ocean to have no obstructions, whereas the Longley-Rice model accounts for all these parameters that are not considered. Now we can model our link budget considering free space path loss, as shown on this slide. We can quickly substitute the parameters for antenna gains and transmitted power into the link budget equation. Furthermore, we take any miscellaneous losses to be zero. This could be a big mistake. But continuing, this leaves us with two values that are unknown: power received and free space path losses. We have to choose a value for one of these to get another, so let's consider some limiting factors for our link. There is line of sight, which would give us the maximum possible distance until the Earth itself becomes an obstacle. We would substitute this into the free space path loss equation. A second option is that we can choose the minimum receiver sensitivity as power received, which would give us the bare limits that link could exist at, assuming no losses besides free space path loss would occur between the two devices. Lastly, minimum permissible SNR value would be taken as a limiting factor. We would find the thermal noise that would affect the system, and using that and the SNR value, we would find our received power. It would make the most sense to use this as our limiting factor, as it takes the environment more into consideration. Nevertheless, each was calculated, and a minimum permissible SNR produced the smallest distance of the three limitations. Therefore, we designed our system using the SNR. Using the 802.11a standard that the packet error rate had to be at least 10%, meaning every 10 packets, one fails. And knowing each packet is 1024 bits, 10 of those packets divided by one erroneous bit gives the bit error rate of 9.766 by 10 to the negative 5. Using a BPSK graph for a given bit error rate, the signal-to-noise ratio was found to be 9.5, producing a receiver power of negative 91.2324 dBm. And following through the calculations, we see that our maximum distance between the boat and the router was 16.8 kilometers. Likewise, following the same method to find the links between each router acting as repeaters, the maximum length between adjacent routers were 18.89 kilometers. Disappointingly, inputting these lengths in the simulation produced a larger received signal power of negative 104.87 dBm. We can see that an extra 13.5 dB was considered in the simulation in obstruction losses and statistical losses. This pushed our negative 91.23 beyond the negative 97 dBm limit, signifying our link would fail. By playing around with the simulations, it was found that a length of 11.52 kilometers from boat to router would have produced a link whose received power was at the negative 97 dBm sensitivity. This would be our final design of the network. Simulations have indicated signs of body losses amongst other losses, such as statistical losses, were present in our system. These losses were unaccounted for in the design. By utilizing lower frequencies and bandwidths, the system would be able to have larger link lengths, as they are less affected by heat and additive white Gaussian noise, though they would have a lower throughput. This concludes this podcast. Thank you for listening.